Okay. Hello, everyone. I'm Ilya Maksmets, one of the OVS maintainers and OVM developer. So, is it better? Okay. Thank you. Today I'm going to talk about stack utilization in OVS and different parts of OVS, including user space and kernel, uh, in context of processing complex protocols like OpenFlow and Netlink. Uh, so let's actually start with just general thoughts about what's the stack, why we need it. Processes in computer systems allocate memory in different ways. There are registers, stack, there is heap, some other stuff maybe. Generally, stack is one of the most efficient ways of allocating large chunks of memory because when you allocate the memory, is basically just a single operation on a modern system. Just subtract some number from the stack pointer, and you get yourself a good chunk of memory that you can use. The problem with stack, however, is that it's quite limited. On a modern system, you may see like 8 kilobytes, 8 megabytes or 2 megabytes of stack memory in user space for the process. This is dictated by the way it is allocated. It's pre-allocated for the process for the thread at the beginning of the thread creation, and it grows usually towards all other stuff in your memory. So it can be extended for the main thread of the process sometimes, but generally it's not a guarantee and may not be possible. So I'm going to just talk about generic things for a little bit. How the function calls usually treat stack. When you call a function, it will push some general context onto stack. Then it will allocate a space for local variables for this function to use. Then we'll do some work, deallocate this local stack space back, restore the context, and then return from the function. And there are different issues that may arise in the process. Like compilers tend to optimize function calls because function calls are generally slow due to all of that processing, extra overhead. And sometimes those compilers over-inline functions, and this part of allocating space for local variables becomes bigger. Even if the function is not being called, the function that contains a function call will allocate more space for local stack variables, even if it's not used. And if it's a large space, it may become a problem in the end if we are running out of stack. So let's look at OVS and what we actually have. We have two main protocols in OVS. First is OpenFlow, that OpenFlow controllers or users directly are using to configure general logic of the network in OVS. And we have Netlink protocol that's OVS itself is using to configure the data path, to install some flows into the kernel and configure the logic on the kernel level. So let's take a closer look at the Netlink protocol. Usually you have Netlink attribute. When you send commands to the kernel through Netlink, you usually send it in the form of Netlink attributes. Each attribute has a length, type, and some data of that length. They can be nested, multiple different types of Netlink attributes can be put into one another, and nesting actually doesn't end until you hit the common limit for the size of this netlink attribute. So the length field here is usually 16 bits. So you are limited to 64K in the total size, but you're not generally limited in nesting of this thing. Here's one example. If you're trying to install a very simple data path flow with input port 18 and actions drop, OVS will produce an link command with the following two attributes: flow other key and flow other actions. First one will contain a nested key for input port, and the second one will contain nested action utter drop with drop explicit reason. Here is a little bit more involved example, even though it is still very simple, but we now have three nesting layers here. We have our actions. Actions contains set masked action, and it contains TCP attribute with some actual data that we are going to use. And what we actually need to do in the kernel when we receive this kind of message, we first need to parse it in order to validate and enrich the data. We need to make sure that it's correct, so users do not send something bogus to us in the kernel. And we need to, some actions require extra metadata for the kernel to store, so they will be enriched with this information. And we, of course, next we'll need to execute when we actually have the traffic passing, hitting this flow. Of course, all of this is done recursively in the kernel. There are better, maybe, ways of doing that, but usually if you unroll recursion into linear iteration, it doesn't look very pretty, let's say, and people tend to not write linear iteration over recursive structures. So that's what we have. As I said previously, netlink attributes length is 16 bits, 64K maximum size, so it's limited, but it can fit a lot of nested attributes. Flow keys usually do not allow a lot of nesting. They are quite linear, unless you use encapsulation, but it's also quite limited. So it's generally not a problem. However, actions are. If we, here's, you can see an example of multi-nested clone action with a drop inside, and you can fit a lot of them in 64K maximum size.
You do restrict how deep you can nest the actions.
We'll get into it. We'll get into it. So yeah, our solution is, well, we just don't do it. We have max depth of 16 in the kernel, but actually it's a very recent restriction. It was introduced not that long ago, reported by MicroVN folks, I think. I should have added some links to this slide. I'll probably do that once before slides are up on the website, but sorry about that. But yeah, for now it's limited to 16, and if we go further than that, then the flow will just be rejected by the kernel, and that's fine. One interesting fact about this is actually user space data path also talks netlink. Communication between OF proto layer in OVS and the user space data path, also known as the PIFNet dev, is also happening over netlink. And there are no such restrictions in user space data path. However, it's probably not a big deal because in users, while we do not really control what's happening with the kernel, like someone else can send a large action list to the kernel and crash the kernel if we run out of stack. But in user space, it's happening all within the same process, so it should be generally fine unless OVS itself generates something funny, which might happen, but just keep in mind. So the kernel stack size is usually 2 pages. So it's on most systems it will be 16 kilobytes. So we can't really go too deep into recursion, and we should not spend a lot of time on one packet as well. So it's kind of justified. We don't really want to go deep into recursion. Packets are running through the data path till completion. And if we spend a lot of time processing one packet, everything else in the system will suffer. So let's look at a simple example of action execution in the kernel. It's just a picture, not representative of anything specific. But let's say we have a few actions and the clone action in the data path and a few more actions in there. First, we'll execute the first action and the second one. That's logical. Then they go to the clone action. We will clone the SKB, clone the packet in the kernel, and start processing those cloned actions. And then they go back to the action tree. And that's all fine. Let's look at the more involved example of the same thing. What if we have multiple nested clones? It's still a single data path action list. It's just expanded in this way. But we do those recursive calls. So everything on the same line is executed sequentially, like linearly, and everything that goes to the arrow is executed recursively. What happens next? We have OVS recursion limit of 5 in the kernel. But we also have, I never actually seen hitting the recursion limit. I'm pretty sure we can, but it's probably in some rare conditions. The main thing that we hit usually is the deferred action threshold. And what happens when we hit deferred action threshold of 3? You can see in this picture that we have 3 recursions already. So we are now reached the threshold of 3. And instead of executing all these cloned actions, we will put them into the deferred actions list. It's a first in, first out queue of a size 10. So in this case, after this action 11, the clone will not be executed. We will copy the SKB, we will copy the action list from this clone, and we will store it in the kernel. And we will proceed to action 12. After the action 12 is executed, we'll go back, hit another clone, now action 9, action 6, then action 3. And when all the actions are executed, only when they go to the first action from the deferred action list. And we start executing those. If we have more clones on this last level, all of them will go into the deferred action list one by one. And what happens if we run out of deferred actions list? Well, the packet's going to be dropped at this point. So we have, as I said, recursion limit 5, deferred action threshold 3, deferred action FIFO size 10, and these are all the warnings that kernel will give you when it drops a cloned packet. You may have seen those in your kernel logs, so you may be familiar with them. Maybe now you understand a little better why this is happening and how exactly it works. It's not a perfect way of executing actions. But as I said, we are working in a tight restrictions of having to not recurse a lot and having to actually execute on every packet fast. So let's go back to our picture. The second and maybe the main protocol for OVS is actually OpenFlow. OpenFlow is executed in user space, so we have a bit more room. In user space, we usually have something between 2 to 8 megabytes of stack by default in the modern systems. So it's quite a lot in comparison to 16K in the kernel. But our processing is also much more complex. We have much more complex rules. We have resubmit actions. We have recirculations. We have contract, whatever. We have 254, I believe, usable OpenFlow tables that we can go through. However, if you notice, it's the same picture that I used for Netlink. In general terms, it's practically the same. We have the clone OpenFlow action in OVS. So I'm just reusing this. It's a single OpenFlow rule executed the same way. It must fit into a single OpenFlow message. Single OpenFlow message also limited to 64K bytes. So it's good. It's kind of limited in that sense. And we assume that we can always translate the single OpenFlow rule as a whole. However, we still check for nesting at some point. And the def check here is 100. 100 is quite a lot, but it's mostly just a check that your OpenFlow rules are actually doing something meaningful. If you have 100 nesting levels, they're probably not doing something right. So the main concern with OpenFlow is actually jumping between tables. We have multiple actions in OpenFlow that can go between tables. These are generic go table, resubmit, contract can jump to a different table after execution, and output to the patch port is actually not going to a different table, but it's going to a different OpenFlow pipeline entirely in a different bridge. So I put it here just in case. The interesting thing about all this is OpenFlow standard, OpenFlow specification is actually good in terms that go to table action, which is the only one which is actually standard action here, can only jump forward. It cannot go back to smaller numbered tables. And that limits how much we can recurse, that limits how much we need to process. However, resubmit, contract, whatever else can jump back. And if you can jump back, you can loop forever, essentially. So while translating the flows, we have to have limits because we can loop forever. One of such limits is max depth is 64, and max resubmits it's 64 squared. The problem with that is we only count towards depth the moves to a different table when the ID is smaller. So this depth is not an actual recursion depth, but the number of times we jump back in the OpenFlow pipeline, which is maybe quite a bit. If we have 255 tables, just for a round number, and if we go through all of them, then jump back, all of them, and jump back, and we have only 8 megabytes of in this case, it's only 8 megabytes of stack. We will have to process every rule in only 512 bytes of stack. And 512 bytes is not a lot. And what's counted towards resubmits? Resubmits are counting any jump to a different table. So not only jumps to backwards, but also forwards. However, it doesn't help much. If we have 8 megabytes of stack, we'll only have 2 kilobytes per rule in this case. And same 512 if we have 2 megabytes of stack. On some systems, we have those. And here are messages you're probably also familiar with, getting from the flow translation when you go over translation depth or over the resubmit limit, which is maybe the most famous one. So 512 bytes of stack per OpenFlow rule is not a lot when we have our basic struct flow that we use all the time during flow translation is more than that, and our struct match is way more than that. So we need to be very careful on how we allocate those structures on the local memory on the stack, and we need a generic solution. And we probably need a generic solution that takes into account the real stack usage, not just arbitrarily numeric limits, but a real stack usage, because every OpenFlow pipeline is different. Every compiler is different. When we produce code with different optimizations, we will have different amount of stack used. Every system, every platform has different stack available for systems by default. So it's all very complicated. I listed here the commit that Mike did good work of reducing the amount of stack functions are using during flow translation in OVS some time back. But we still need some generic solution to avoid crashing, basically, which happens. So here we are now in the proposal territory. It's not something that OVS does, but I hope it will. It might be in the next release if I'll find enough time for this. But yeah, one basic idea is to actually track the stack size. It's not very handy to do in general in C, but compilers do provide some built-in functions, like GCC and CLang provide built-in frame address function. Note it's only safe to call for the current stack frame. GCC documentation says that if it's called with any other stack frame, it might crash your program, so don't do that. But for the current stack frame, it should be safe. So we can record what's our current stack address. And if we record the base address and then we check again, we can check the difference and see how much stack do we actually use. And we can know how much stack do we actually have by asking pthread get stack size, like standard pthread function. And what to do about it? Well, we can trigger a recirculation when the stack frame address is close to the base frame address plus stack size. So basically, when we are about to run out of stack, we can trigger recirculation. This will install the data path flow into the kernel, and then we can restart the processing. So I have 1 minute left, and I have one last example of how it does. Assuming we have 3 tables, we're jumping between 3 tables with resubmit, and let's say we are running out of stack on the 3rd one. So when we try to resubmit to the 3rd table, we check the stack size, and we are out of stack. What we do? We freeze it. We save all the actions that's supposed to be executed after resubmit. So resubmit itself, action 9, action 6, and action 3, which are not yet executed. We can store them, we can store the flow key, some other metadata, and we can assign an ID. And what this ID is our recirculation ID, which you're probably familiar with. So OVS stores this kind of frozen state per recirculation ID in memory. And whenever it gets a packet with this recirculation ID, it can restore the metadata, and it knows where it should continue the processing of the packet in the OpenFlow pipeline through this frozen metadata. Exactly the same process. So this works exactly the same for contract, for other actions that require recirculations. This works exactly the same for packets that have to go to controller through pause and resume. So if a packet has to go to the controller, it will be frozen state will be captured. It will be encoded, sent to the controller. Then controller sends it back. We can restore it and continue processing from where it left off. And yeah, that's it. Any questions?
I think we have short time for like one question. So
Hi. Can you please go back to the last slide? So why don't we just process it in like Act 1, Act 2, resubmit, add it to memory, Act 3, and then like just do it in different order altogether if we already trying to do it just for some cases.
So you mean to just mimic what we do in the kernel and have our deferred actions stored?
Always do deferred actions, basically. Why don't we do it?
Yeah, it's an interesting question. I don't really have a good answer for it. We can do it this way. We can either recirculate, or we can execute them right away once we get back from the stack. However, I think it's more beneficial if we just store it and then execute later, because this way we are freeing ourselves for translating something else. So if we have a lot of flows to translate, then we can interleave those parts, and we don't have to spend a lot of time on a very large flow blocking all other processing. One example for this maybe is usually such very big pipelines are for like a single packet. For example, in OVN example, you can, if you attach a router to multiple networks and send an ARP, it may be resubmitted to a huge number of switches attached to it. And this only happening for ARP packets. So basically 1 out of 1,000 packets will trigger this. And if, or maybe even less. So what we would like to do, maybe we could stop this processing, stop wasting resources, execute in the kernel what we can execute right now, and keep going with other stuff that we have, other packets queued waiting for processing, which may be faster. So maybe in terms of latency, maybe a better solution this way. But I didn't really test, so it's a good thing to try and test. So thank you.
all right, let's thank our speaker one last time.